So the first event is you choose a coconut almond bar first. Event B is you choose a cranberry almond bar second. All right, so this is kind of one of those gray zones in math. There's less like certainty about some of the probability things. So this one, there's a few things like I think about when I read this, and I'm probably overcomplicating it. But what you're really wondering is, is the second event impacted by the first event? Okay, so a scenario where it would be impacted is like, let's say there was only a cranberry bar in the box, and you chose a cranberry bar first. Well, then you can't choose one second. We don't really know what's in the box, which is kind of the vagueness of this question. Maybe this is just one of those sort of, let's see what you come up with type of problems here. It's almost easier for me to tell you what things are independent and then to come back to this.
Yeah.
So we'll look at that for the moment. We'll come back to this and talk about it. So things that are independent would be like a coin flip. The outcome is independent each time. Rolling a dice. Okay, so there's certain things we know that are independent, where the outcome of one is not impacted by another, or when you do something else does impact it. A spinner, that's generally independent. Some things like that. So the thing that I'm struggling with here, because you're taking the bar out and you're actually eating it, that means there's one less candy bar
Right.
in there. And that's why I would tend to reason that these are dependent, because the taking one out impacts your likelihood of selecting another.
Right.
So that's the wording your teacher's looking for. The wording is, it's dependent because event B may be impacted by event A. Basically, the probabilities change when you take one out and eat it. Now, if you take one out and put it back, that's a different story altogether. But that's not what's happening here. It's taking it out, eating it, it's gone.
Yeah.
It's like when you go family dinner and you want a certain piece of pie, somebody gets it before you, it's not there anymore. You can't eat it.
Right.
So what you want to ask yourself is this question: does the outcome of one event affect another? That's kind of your overarching question that you're asking.
Okay.
And these will go faster. Just starting to give you some information before we go. Start
Right.
jumping into them. All right, so number 4 is a very like, this is the one I wish we'd started with, because you could sit there and flip a coin, and I can roll dice. We're not even anywhere close to each other, and one does not impact the other. Like, we can physically see that. Like, if you get a tail and I get a 3, they're unrelated.
Right.
Like one does not affect the other, and it's easy to see that because we're physically apart. But even if you were in the same room, the same thing is happening. Now you could sit here and argue like, well, what if I bounce the dice into the coin? Like, it's not what we're trying to do here.
Yeah.
So these are independent, and it's the reasoning is almost the same as the other. It's just saying that one does not impact the other.
Right.
So and so this next question I think is a little outdated here, because we know that actually, I mean, well, I don't know, when you like do a Spotify list or you go listen to something on there, it sort of plays into what you like or don't like.
Mhm.
So this you can't think about this problem this way. You have to think about it as if you randomly choose a song and then you randomly choose another song without repeating song choices. So that's important. Are these independent? Okay. Basically, you're asking, does the selection of one impact the selection of another? If they're if one impacts the other, that's how, again, how you think about it. Since they're random, it's like, imagine there's a bucket and you play a song, but it says that when you randomly choose another song, like it's not impacted by the fact that you already chose one.
Right.
So I guess I would sit here and say that these are independent because of that language they're repeating song choices. All right. 6. So this one at first glance might appear to be the same as number 5. It says that there are 22 novels of various genres on a shelf. You randomly choose a novel and put it back. Then you randomly choose another novel. Well, actually, I take that back. Because of the randomness matters, I guess, is the point here. Like normally when you take a book out off the bookshelf and read it and put it back, you wouldn't go and grab for it. But it's as if you're blindly grabbing for another book without knowledge of the previous one.
Right.
So these would again be independent. It's also important that you're putting it back.
Exactly.
Is this your first exposure to probability in math, or did you see this in another course?
Yeah, but I mean, maybe in like middle school we would do like kind of something like this, but never anything this far.
Sometimes they touch it in other classes. So that's why I ask. There you can take whole classes in this. There's advanced, you can get advanced degrees in this stuff if you like it.
Yeah.
Any questions on what we did so far?
No, we're good.
All right, so determine whether the events are independent. You play a game that involves a spinning wheel. The section of the wheel shown has the same area. So that's important. The reason it's important is that each outcome is equally likely. Use a sample space to determine whether randomly spinning blue and then green are independent events. So a couple things here to talk about. The sample space is often written as a set. So a letter, capital letter, is used to define a set, and then these curly braces are used to enclose the outcomes of the sample space. And so we can use like the first letter blue, red, green, and yellow to denote that.
Right.
So that's the first thing. Is that okay?
Yeah.
And if you don't like letters, I mean, you're more of a number person, you could do this. You could just label them with numbers as well. Okay.
Yeah.
Question is like, is each spin independent? Okay. And try not to think of it in terms of like, I don't know if you ever watched Wheel of Fortune where people are like able to spin to the exact place, or at least the host seems to be able to. Which is kind of impressive, but I guess if you spin the wheel, a bunch of times, you get pretty familiar with it.
Exactly.
It's like you're just randomly spinning, and you're not trying to influence the outcome. Each one is equally likely. Like there's no bias. Maybe that's another word you might have heard here. So these are definitely independent events.
Yeah.
All right. Let me know when I can move to this one here, if that's clear.
Yes, you're all good.
All right. You have 1 red apple and 3 green apples in a bowl. So I sometimes will go, okay, I've got a red, green, green, green. You randomly select one apple to eat now and another apple for your lunch. Use a sample space to determine whether randomly selecting a green apple first and randomly selecting a green apple second are independent events. So the sample space here is, you have to write this in terms of your first outcome and then your second outcome. Okay, so what I mean by that is you could choose the red apple and then this first green apple. I'll call it green 1. You could choose the red apple and then green 2. You could choose the red apple and then green 3.
Right.
Okay. And sorry, maybe I missed, these are merged together. There's not a comma here. They're kind of together. But then you could also get the first green apple and then the red, the first green apple and the second green apple. You could get the first green apple and then the third green apple.
Yeah.
Okay. This keeps going here. So the next possibility is that you could get the second green apple and the red, the second green apple and the first green apple, the second green apple and then the third green apple. And then similarly, you could get the third green apple and then the only red, the third green apple and the second green apple. Or sorry, first green apple, and then the third green apple and then the second green apple. And this is the sample space. This is like what could happen. And maybe you didn't think there was that many possibilities. A lot of them are overlaps though, because you don't really care whether it's a green first, second, or third. You just care whether it's green. Does that make sense?
Yes.
Okay, so like in reality, the real sample space is a little bit smaller. It's you can get a red and a green and a red, or you can get a green and a green. But in terms of like the actual, how many of these do you get? There's only 1, 2, 3 red greens. How many green reds are there? There's 1, there's 2, there's 3. And then the rest are green greens. I believe there's six of those. Is that okay?
Yes.
Okay, so what this means is, what are you most likely to get here? You're most likely to get green green. Okay, the probability of actually getting a green and then what does it ask for? Determine whether green apple first or independent. So the answer is no. I mean, like one does impact the other. If you take a green and you take it out and you eat it, but the sample space here is there's kind of 2 ways to write it. Like the first one's kind of more correct. The second one's kind of getting to like probability. So like the probability getting a first red and then a second green is 3 out of 12. A first green, 3 out of 12, and then 2 greens is 6 out of 12. Anyway, I believe that these are dependent because the selecting of one impacts the other.
Right.
So you could say it much more simply than I did.
Okay.
Probably the most important thing we're doing besides the independent and dependent is like writing the sample spaces. So the sample space here, it does matter. That's why I'm writing it down here. But let's take a look at this question. It says a student is taking a multiple choice test where each question has 4 choices. The student randomly guesses the answer to the 5-question test. Use a sample space to determine whether guessing question 1 correctly and question 2 correctly are independent events. So rather than trying to think through this in terms of like sample space, it's almost better to look at it in terms of, does one impact the other? Does guessing on the one impact your answer on the other? What do you think here? What do you have to say?
Let me read it again as soon as I feel like it might be independent.
Yeah, now it's much simpler than this, than the way it's written here. It's literally like you guess, you flip a coin, heads or tails, you flip it again, it's independent. When you guess on the first question, you don't know whether you're right or wrong, so you don't have any way to like,
Control it.
yeah, you don't know whether like, okay, I'm gonna guess again. Like, you don't know whether your guess helped you or hurt you on the first question. So these are independent. Now, and now in a real, real situation, like think of this as a computer randomly guessing these. But as a human, like we are biased. We do think, okay, well, if I guess C on the first one, I probably should not guess C on the second because it's probably not C and then C is one way to think about it. Another way to think about it is, well, maybe if I guess C every time, I'll at least get one right.
Right.
Okay, so we as humans, we are very biased. But think of this as a computer or machine or a spinner. Like think of just spinning that one we had earlier. Use that to make your choice. And that is truly independent when you spin.
Yeah.
So in terms of your sample space here, you can think of it as right, wrong. So you can either get the answer by guessing. You could either be, let's say, correct, 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 wrong, wrong, correct, wrong, wrong. And the question is, well, what's the most likely outcome? What's most likely here? Well, if you go to actually like within the question, like the question itself has A, B, C, or D, and then the
Right.
second question is A, B, C, or D. You could guess A, B, A, C, A, D. And then for the next, you could also guess B, A, B, 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 C, B, D. And then C, A, C, B, C, 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 D, D, A, D, B, D, C, D, D. There's only one possibility out of these 16 that you're correct. Like there's only one sequence of where you get both letters correct when you're guessing.
Yeah.
Whereas more of them are going to be, okay, you got one right, but one wrong. Which one did you get right? Well, let's say you got the first one right, but the second one wrong. Or what if you got the first one wrong and the second one right? There's a little bit more there, but most of the time you're getting them all wrong.
Right.
And so the probabilities when you get to that will help influence this. Like you might even look at these questions one more time when you're doing probabilities. Basically, like, yeah, one impacts the other. I'm sorry, one does not impact the other. They're independent, and you're probably going to get it mostly wrong when you do this, unfortunately.
Yeah.
So don't guess, basically. Use
Yeah.
use another approach. Maybe try the problem out. All right. All right. Vase contains 4 white roses and 1 red rose. So we've got white, 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 and then a red. You randomly select 2 roses to take home. You sample space to determine whether randomly selecting a white rose first and randomly selecting a white rose second are independent events. So again, because you're taking them out, that's typically always dependent.
Right.
The sample space here is you could take home a white and a white. You could take home a white and a red. You could take home a red and a white. And that's it. Okay. Now the thing though here is that since you're taking them both home, the second two are actually overlapping. Like you
Right.
don't really care whether the order is. You don't care that first one was white, second one was red. But again, in this problem, because taking one out impacts the selection of the second, they are dependent events.
Yes. Okay.
All right, it's number 11 here. Maybe this is the last one. Okay, now you actually have to start finding some probabilities. That's good. All right, you play a game that involves spinning the money wheel shown. You spin the wheel twice, find the probability that you get more than $500 in your first spin, and then go bankrupt on your second spin. Okay, so what I can't read and what I can't really see, and I think maybe you can help here, is we need to count how many of these are more than 500. So
Right.
the picture's a little grainy. That's what I'm asking here. Like I don't know which ones. Like I believe that one's okay, but this green one is not. Is this 650? I don't know if you have a better on your screen, maybe on your
Yes,
computer.
it is 6.
Okay.
Wait. Yeah, 650.
Is this 750 down here?
Yes.
And I can't read the next one. It's either 800 or something else.
I think it's, wait, let me see which one you're looking at. To go back to the blue one you're pointing at.
Well, I think the blue one's okay. Basically, I guess I'm just going to ask you to count the ones that are more than 800, more than 500. So if they're 500, it's bad, but more than 500, how many do you see there?
There's a 750, and then a 950. And then there's another 700. There's a 500. There's a 900. And then another 700, and then a 550. And that's, I think that should be it.
All right. So how many total was that?
So count the amount of how many are over 500.
Yes. Yes. How many? Could you just count that for us?
Yeah. Is that one 5,000? I think it's 5,000.
Yeah, that one's 5,000.
So 1, 2, 3, 4, 5, 6, 7. I want to say 7.
Okay. I can't see this. So if you need the correct answers.
Yeah, it's kind of hard. So
yeah. I'd recommend going back to whatever you took the screenshot or picture from and checking. Now the total number of places is 24.
Yeah.
Okay. So that's probably more than 500. The probability of going bankrupt on any spin is however many bankrupts there are, which there appear to be 2 out of 24. Would you agree with that?
Yes.
Okay. Now, when it says here, you find the probability that you get more than 500 on your first spin, and so typically and in this part of the course corresponds to multiplication. So you're going to take your probability of your first event, 7 out of 24 for getting more than 500, and you multiply it times 2 out of 24 like that. And that's your probability. So you take the probability of the first event times the probability of the second event.
So it would be 14 out of 24.
You're multiplying, so you have to multiply that
Or
bottom number.
24, sorry, 20, 24, yeah.
And then, you know, you can reduce this, you can make it a decimal. This is where you got to ask your teacher, you know, what they want here. Sometimes they want both, sometimes they want one or the other, but that is the answer.
Okay.
All right, so this is the next few problems are kind of more what I expected to see, not so much emphasis on you know, independent and dependent, but it does impact these problems here. So that's probably why you had it. So it says you play a game that involves drawing two numbers from a hat. The numbers are 25 pieces of paper numbered 1 through 25 in each hat. Each number is replaced after it is drawn. That's very important. So in the hat here, 1 to 25, that's 25 total. You take one out, but then you put it back in. Very, very important here. So find the probability that you will draw the 3 on your first draw, and so that means multiplication, a number greater than 10 on your second draw. So the probability of drawing a 3 is how many 3s are in the hat. How many 3s are in this hat? They're numbered 1 to 25.
So 3.
There's just one.
Oh, I thought you meant like the number 3, like how many times is
Yes,
it?
just one, just a 3. Like there's a card with a 1 in there and a 2 all the way up to 25.
Okay, so just one.
So 1 out of 25. Okay. Now, since you're you draw it and put it back in, there's still 25 left over. So greater than 10, how many numbers are greater than 10 inside here? So that's 11, 12, 13, 14, 15. Sometimes you write all these 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So there are 15 numbers that are greater than 10. Is that okay?
Yes.
All right. There's 25 total. The reason there's still 25 total is because you didn't take one out. You didn't take that 3 out.
Oh. Right.
All right. So now because it's an and, you take the first probability and you multiply it by the second probability. So this is 15 over 625. It does reduce. You probably at least ought to give it the reduced form. You're back to kind of being able to use your calculator now. Like they don't frown upon that as much.
Right.
Whereas, you know, when you can just graph the problems, it's maybe. So just to be clear here, the probability is like the event that you care about, like what you want, like whichever events are okay, and then over the total possible outcomes.
Right.
And let me go back actually and reduce this one here as well. Believe it just, yeah, just divide by 2 like that. Any questions on that before we move on to 13?
No, let me just finish writing that down.
Okay.
Okay.
Right. 13. All right. A drawer contains 12 white socks and 8 black socks. You randomly choose one sock and do not replace it. Okay, so that's important. That means they're dependent. If you then you randomly choose another sock. Find the probability that both events A and B will occur. Okay. Event A, the first sock is white. So what you're trying to think about is, well, how many white socks are there in the drawer?
Well, it says 12.
There's 12, and that's what you want. Like you can grab any one of those 12 and you're good.
Right.
And on the bottom is the total number of socks. How many socks total are there?
20.
20. Okay. Now, the next one is the second sock is white. All right.
Right.
So this one assumes, though, because the way it's written, it says find the probability that both events A and B will occur. So it assumes you chose a white sock first. Okay. So if you choose a white sock, how many socks are left in the drawer? Just total. If you choose,
So if you choose one white sock,
yeah, how many socks are left over in the drawer?
19.
19. That's your total. What do you want this time? You want a white sock again,
Right.
but you already chose a white sock. Okay. So how many white socks are left over after you choose a white sock?
11.
11. I'm asking these questions because it just going through it first time, it's just gotta be very clear. It's 12
Right.
because there's 12 to start. There's 11 because you chose one.
Yeah.
There were 20, but you physically took one out, so now there's 19. And you assume, it says here to assume that event A occurs before writing event B. All right, now the probability of both events is the multiplication of them, 12 over 20 times 11 over 19. So it's a probability of A and B taking place
Right.
here.
Yeah.
All right, so that ends up being 33 over 95. You can grab a calculator if you want to reduce that further. Let me know when we can move on to 14.
We're good.
Okay. A word game has 100 tiles, 98 of which are letters and 2 of which are blank. Okay. So they're showing you here there's 9 A's and 2 B's and so on here. The number of tiles in each letter is shown. You randomly draw one tile, set it aside, and then randomly draw another tile. Find the probability that both events A and B will occur. So event A, the first tile is a consonant. Okay. So there's a couple of ways to do this. One is to literally add up all the consonants. Okay. But we know that there's a lot of consonants and there's not as many vowels.
Right.
Right. So the total is divided among vowels, consonants, and blanks. Okay, there's 2 blanks. So what I propose, and because we know the total is 100, what I propose is we add up the number of vowels, A, E, I, O, U, and then the number of blanks and subtract from 100, rather than adding up all the consonants.
Yes.
Do you agree that that will work? Are you okay with that?
Yeah. Good.
All right, so the vowels A, E, I, O, and U, we got 9 plus 12 plus 9 for I, O is 8, U is 4, and there's no sometimes Y. I believe it's just the typical consonants here. So that's 9 plus 9 is 18, plus 12 is 30, 38, 42. So there's 42 vowels, 2 blanks. If we subtract that from 100, we should get 56 for that.
Right.
So you can go back later and add them up if you want, but that's how we're doing this one. So we want the probability of a constant first. There's 56 consonants out of 100 total. $56 out of 100.
Yes.
Okay. Once we take one out, though, how many tiles are left over? Total tiles are left over.
So when you take how many?
You're taking one out. Like you reach in the bag and you pull one out. How many tiles are left over inside the bag?
Oh, 99.
Yeah. Good. It's really important that you see that on dependent events, that bottom number goes down. Now, the second is a vowel. Did we grab a vowel the first time? It says event A is the first letter is a constant. So are we changing this number 56 or are we using a different number altogether?
A different number, right?
Yes. We're using the fact that there are 42 vowels.
Yes.
Okay. All right. So event A, probability of A and B is 56 out of 100 times 42 out of 99. And this one almost certainly you'll want to round to nearest decimal, probably. I mean, you can ask your teacher what they want. I mean, it is a fraction, but we'll do this point. And how many decimal places? I don't know. This is where you ask your teacher, how many decimal places? I don't know.
And he's pretty like nonchalant about those. Like he won't mark you off on a test.
Oh, good. Yeah, I mean, unless they specify, you should be okay. All right. 15, error analysis problem. So we've done a few of these where it's asked for the probability of A and B. And if you haven't figured it out by now, it's the probability of A times the probability of B.
Right.
So the error here is that you're not multiplying. Like they just add here. They should be multiplying.
Mm-hmm.
And that will do it for that.
Oh, yeah. Yeah.
All right, for 16 here.
So for that last one, it should have just been 1.2 or
Which one? The
like for
vowel.
15, it should be 0.6 times 0.2.
Yes.
Okay.
So my preference here on these error analysis problems is to actually do just to do them without looking at it and then comparing to what they have. So shelf contains 3 fashion and 4 health magazines. You randomly choose one to read, set it aside. That's very important since you set it aside, and randomly choose another for your friend to read. Describe the error. Okay, so let's just go through it. Event A, the first magazine is fashion. How many fashion magazines are there?
There are 3.
There are 3. And how many total magazines are there?
There are 7.
7. Okay, so probably a fashion 3 out of 7. Now you assume that you took a fashion magazine. That's very important. Usually you can't assume things, but here you do. You have to go down this sort of like path of like, well, what's happening? The health magazine here, well, there's 4 health magazines, but in terms of the total, you took one off the shelf and you didn't put it back. So how many magazines are there on the shelf?
Seven.
There were 7, but you took one and
Oh,
threw it
6.
in the trash. 6, yeah. So in these sort of sequential events like A to B, you typically almost always go down by 1 on the bottom.
Right.
Okay, so the probability of A and B is 3/7 times 4/6, which is 12/42 or 6/21 or 3/7. That's what it looks like when it reduces. Sorry, 2/7. Sometimes they do reduce nicely. All right, now let's look at the error. Like, let's see what they did, which we know is wrong because they're telling you to find the error. Okay. So they say the probability of A is 5/7. That's wrong. It's 3/7. There's 3 fashion magazines. So we know that's wrong. Probability of B given A, which is the second thing we found, is actually 2/7. So we know that it's 4/6. So we know that's also wrong. If you need to write that down. This vertical line here means given, which I didn't know. This is for dependent events. But basically they use the wrong 2 numbers for both calculations.
Right. Okay.
All right, well, that's 3 through 16. We got a few minutes left here. Is there anything else you would like to cover tonight or anything else you got questions on?
I think I'm understanding. I think you did a good job explaining it.
Well, thank you. I appreciate that.
You're welcome.
I mean, I'm okay to stop a few minutes early. It's up to you. You're the customer. If there's anything else you'd look at quickly or not, it's up to you.
Yeah, I think we can end it here.
Okay. Sounds